you heard a little bit about some of the neural network architectures earlier and some of the hyperparameters that you come across in deep neural networks. But stepping back for a second, in general, hyperparameters are your model's magic numbers. Hyperparameters are values you set as part of your model before you begin to train with any data. Examples from neural networks are the number of hidden layers in a deep neural net. This could also be something like parameters of your model, like the number of trees in a random forest. And hyperparameters have a large impact on the performance of your model. Tweaking the values by a small amount can have an impact both positive or negative on how well your model performs. Hyperparameter optimization, hyperparameter tuning, model tuning, and model selection all refer to kind of the same general concept, which is the search for the values of these hyperparameters that cause your model to perform the best. And the way you perform hyperparameter optimization is kind of with this iterative process. You kind of have an optimization method that suggests the next values for hyperparameters. You reevaluate your model, and then you have some measurable observed model performance. And then again, your hyperparameter optimization method will suggest new values for the hyperparameters to try. You'll evaluate your model again, and you'll again observe the model performance. And at SigOpt, we call this the optimization loop. And the reason why I get so excited talking about hyperparameters is because you can see amazing performance gains with hyperparameter optimization. These are all examples from the SigOpt blog where we built a model, TensorFlow, XGBoost, recommender system, and then we use SigOpt. SigOpt is an optimization service. We use SigOpt to optimize the hyperparameters of the model. And this is the difference in performance before or after hyperparameter optimization. For TensorFlow, there was a 315% boost in accuracy. For many of these models, hyperparameter optimization was the difference between kind of a scrappy prototype and something that's production ready. But what becomes concerning is that many people miss out on the true performance gains of hyperparameter optimization because they fail to implement the necessary steps beforehand to perform hyperparameter optimization correctly. And so what I'd like to do in my talk is drawing on my experience building an optimization service at SigOpt and what I've seen from people using it, I'd like to go to address some of the common problems in hyperparameter optimization and show you a few solutions. The biggest mistake in hyperparameter optimization is not performing hyperparameter optimization. Some people think they can get out of it. You know, in that optimization loop, you are getting values for hyperparameters, explicitly setting those values on your model, and then observing your model's performance. Well, if you're not explicitly setting hyperparameter values on your model, are you really kind of on the hook for the values of your hyperparameters? And the answer is yes. By not setting hyperparameter values on your models, you are explicitly choosing kind of whatever the default values are that the developer who implemented the model selected. And your default values may not always be the best choice for your model. And this is especially true for deep neural nets. You saw that 315% accuracy gain for TensorFlow. That was because we were learning the architecture of the model at the same time as we were learning the model weights. And oftentimes the default architecture choice for deep learning models may be incredibly inappropriate for your problem. And this actually is an example from a recent hackathon where I was trying to build a model, and I used the default values for my entire pipeline. I used the default values for word to vec, and I used the default values for a stochastic gradient descent model to build an NLP pipeline. Thought I was doing such a great job. I did my feature extraction, I did my model building, and I looked under the hood, and after I used all my default values, I built a classifier, a binary classifier that just predicted all ones. Kind of a crappy classifier. Kind of a bad classifier. So once you start performing hyperparameter optimization, you need a way to measurably evaluate your model. And this should be aligned to kind of the actual business objective that you want from your model. There's a great example at Microsoft where they were trying to build a search ranking engine. And the way they decided to measure their search ranker was by running an A/B test and measuring the number of searches performed. So they built their search ranking model, they deployed it, they ran a test, and lo and behold, the number of searches overall went up. But when they decided to look at the search results produced by the model, search results were absolutely terrible. And the issue is that they had inadvertently degraded the user experience. And so users needed to search more per session to find the information that they needed. And this is an issue because there was an incorrect underlying assumption that if you measured the model by the number of searches, you could drive up the number of searches and this would also drive up user experience. Well, it turns out that the way they were evaluating the model was inversely correlated with a good user experience. And this is especially a concern in hyperparameter optimization because hyperparameter optimization is all about amplifying the metric that you choose to evaluate your model with. And so if your metric is based on incorrect underlying assumptions, hyperparameter optimization could amplify those incorrect underlying assumptions. Now say you have competing metrics. You're balancing these short-term and long-term metrics to meet your business objective. Say you're balancing something like profit and quality, or something like compute time and accuracy, or you're say choosing where to go to lunch every day. You're trying to balance grossness, effort, and cost. These are all different kind of competing values, and you have choices when you choose to in how you evaluate your model based on competing metrics. You can create a scalar value composite metric, or you can also evaluate the entire space of possible solutions using a multi-metric approach. But the point is, you can balance competing metrics when you choose to evaluate your model, and you have options in how you go about this. Overfitting is the issue in which your model will perform extremely well during training and optimization, but extremely poorly out of sample. You may see that your model performs with like 95% accuracy on a test set, but when you deploy it, maybe only 60% accuracy. And there are some fairly well-known ways of getting around overfitting and helping your model generalize well to unseen data. Cross-validation and using regularization terms, so just adding a regularization term to your loss function, or using backtesting, which is appropriate for time series data, can all help your model generalize better and avoid overfitting. And just to go over a simple example, this is a really simple way of how cross-validation might work for you. You take your data, and then you shuffle and split your data into k different sets, and k equals 3 or 5 is generally a good number. And then you iteratively, for one set of hyperparameters, you iteratively train your model, and then you test your model on that data. And you train, and you test, and you train, and you test. And the overall metric that you report is not your original metric, but the average of these kind of k cross-validated metrics. And if you use this cross-validated metric in hyperparameter optimization, you will be much more likely to prevent overfitting. So one of the large issues in hyperparameter optimization is over-constraining the parameter space. And this is an image that should be familiar to people who have played around with deep learning before. It's from playground.tensorflow.org, Google's in-browser deep neural network. And as Karina was talking about earlier, there's a lot of hyperparameters in deep neural networks. You've got your the model parameters of the algorithm, the hyperparameters of whatever algorithm you decide to use, and you've also got the hyperparameters of the architecture. And as she brought up, these can be incredibly difficult to kind of discover because you've got this this non-convex response surface. So it's hard to just tune one at a time. When you look at all of the algorithm or all of the hyperparameters together, and when you're performing hyperparameter optimization, you're optimizing all of the parameters at once, you are able to uncover hidden interactions between the different hyperparameters. And and achieve a better model because you're exploring the entirety of the surface of the interactions of the hyperparameters. And also when you're building a machine learning, you're not just building a machine learning model, you're building an entire pipeline. You're going from raw data, doing feature extraction, you're building a model, and oftentimes hyperparameter optimization is only bolted on top of just the model building aspect of the pipeline. And occasionally this is because perhaps the pipeline isn't a repeatable process. And there are many different reasons why this may happen. But feature extraction has parameters as well. It's just that the concept of tuning only your feature extraction isn't very well defined. You don't really have a way of going from words to n-grams and then measuring that those n-grams are doing well. You kind of have to do something with them. And so I would encourage you to tune your entire machine learning pipeline at once. Include your feature parameters when you are optimizing your hyperparameters as well. And this kind of builds a better method of performing optimization. We have an example of tuning an XGBoost model where we went and we were predicting MNIST digits. And we measured the model performance for several different optimization methods. And we saw that we had a certain baseline level of performance around like 70% accuracy without tuning with an optimized model before we added in the feature parameters. But when we added in the feature parameters, we achieved a much better accuracy. And so this is a great kind of statistically significant example of how throwing in the feature parameters alongside your model parameters can get you more performance as well. So once you've decided how you want to evaluate your model, you've hopefully thrown in some cross-validation, backtesting, or regularization to prevent overfitting, and you've decided on your hyperparameters. Most people try out just selecting by hand a couple of different values for the hyperparameters, just to see what happens. I want to step back for a second to the optimization loop again. You've got this optimization method that suggests your hyperparameters, and you're iteratively evaluating your model, and then you're observing the model performance. And when you are going and you're selecting your hyperparameters by hand, you are being your own optimization method, and people aren't necessarily good at performing 20-dimensional optimization in their heads. Picking hyperparameters by hand can be time-consuming and expensive. And it's been shown that that algorithms that suggest hyperparameters, algorithmic optimization methods, can beat out years of expert hand tuning within a number of hours or days, depending on how long it takes to evaluate the model. And so by only constricting yourself to hand tuning, you are missing out on perhaps the performance gains that can result from using a different optimization method. And these are just some examples of optimization methods. They're different. Optimization methods all suggest hyperparameters differently. An expert is one optimization method, and there are also other choices out there that will get you different levels of performance on your models, and they should all be considered separately. So, I'm from SigOpt. We sponsored coffee for MLConf, and all of the cups say no grid search on them. So I'm going to go into that a little bit. So grid search, as many of you may know, is when you're kind of iteratively cutting up the space of your hyperparameters into a grid, and you're kind of evaluating on the corners of the grid. And so say you've got say you've got like some continuous parameters, you're maybe choosing like 10 values per parameter, and then you have to decide to, okay, for maybe like parameter A is 1, and parameter B is 1, and then parameter A is 2, and then parameter B is 1. You have to kind of evaluate all these discrete points on a grid. So we're not fans of grid search. We're not fans of grid search because while it may be easy to understand and easy to implement, grid search suffers from the curse of dimensionality. Remember that optimization loop? It requires that you evaluate your model for every different suggestion of hyperparameters. And grid search is a method that is not very careful of the number of times you must evaluate your model. So it quickly becomes intractable when you have problems with 5 hyperparameters. And when you're doing things like artificial intelligence or deep neural nets, you will very quickly have more than 5 hyperparameters. And so methods like grid search become too computationally infeasible to get results. Either you have to drop the number of hyperparameters you have, in which case you will not be able to investigate some of the more sophisticated interactions between hyperparameters, or your grid may become too coarse to be able to get any reasonable results. Random search is often presented as an alternative to grid search. Random search is similarly easy to understand and easy to implement. You just pick random points in the parameter space and evaluate those random points. And surprisingly, random search has been shown to be theoretically more effective than grid search. And I have a references section at the end where I link to the paper by Bergstrup. But random search suffers from a large variance in performance. And random search doesn't take any of the past combinations that have been tried or any of the past results into account. Instead of jumping straight from grid search to random search, there are many more intelligent methods out there that are much more sophisticated that will get you better results than grid search in many fewer evaluations than grid search. So better model performance in many fewer iterations of your model, so less compute resources, with a lot less variance than random search. And these are just some of a few. Genetic algorithms, Bayesian optimization, which SigOpt is based on, particle-based methods, convex optimizers, and simulated annealing, all have packages that have been written for them in the last several years, so that you can take advantage of kind of the most sophisticated mathematics and parameter optimization out there, and you can build those into your machine learning pipeline to tune your hyperparameters without having to have a PhD in mathematics. And SigOpt is an example of one of the APIs that can be used for this. So this is kind of an example interface for one of these intelligent methods. We don't require that you know anything about Bayesian optimization. You simply define the parameter space, and that's one API call. And then you have another API call to receive suggested hyperparameters. And then another API call to report observed performance. So in conclusion, hyperparameters affect your model's performance. Tweaking values of your hyperparameters by a small amount can have a large impact on how well your model performs. So you should definitely be performing hyperparameter optimization. But performing hyperparameter optimization correctly requires certain care when it comes to evaluating a model, selecting your hyperparameters, and selecting an optimization method. I'll be at the SigOpt booth later if you have any questions. Thank you, and happy optimizing.